Let me present. 1 minute. So, yes, you can probably see my screen, and we'll go to the book. Can you see my screen? Somebody say yes. Yes?
Yes, sir.
Yes, sir.
Thank you. Okay. So, so in the last class, we were talking of this block diagram. Do you remember? So, just can somebody tell what is an interfering input? Anybody remembers anything? We can, this type of asking question will never elicit a response because nobody's name is somebody. So, Sumedh, कुछ याद है? Sumedh Lodi.
Hello.
Do you remember what is an interfering input?
Yes, sir. It directly adds to the actual input.
Right. So it is an input which affects the output, but in an additive manner. It creates an error, but it creates an error in the additive manner. On the other hand, the modifying input does what? Somebody, Aman Kumar Sharma. Remember anything?
Sir, it modifies the input in like proportional manner, right?
Yeah, you can make out if you see the diagram. See the effect. It is the effect. It is the error it is producing, which is this added term, is Km Im into I. So it is dependent on the desired input. Therefore, it is actually changing the gain. The gain, effective gain with this path together, you can probably see my mouse, is K plus Km Im into I. So now the gain K has been changed to K plus Km Im. So it changes the gain and it affects the error produced is multiplicative with respect to the desired input. So if the input increases, the error will increase. Here, if the input increases, the error will not increase. The error is constant, right? Correct. So now, there are some examples given in the book. For example, this is the example of a strain gauge. So as I was saying, that the strain gauge takes a strain input and produces a change in resistance. That's just the property of the gauge. So actually it produces a resistance change. It is the resistance change which is proportional to the strain. So the nominal resistance of 100 ohms is added to get the total resistance. And this is the gauge factor, 2 into 10 to the power 2. And the gauge factor changes with respect to, so there is a thermal coefficient of resistance effect. So the resistance changes not only due to strain but also due to temperature. Therefore, temperature acts as an interfering input through this channel. On the other hand, the temperature also affects the gauge factor. So the gauge factor, this is the environmental temperature. So the gauge factor changes with respect to the environmental temperature, And this is also taken into consideration. I think there is a typo here. It cannot be 2 into 10 to the power 2 for a 1 degree centigrade environmental temperature change. Gauge factor doesn't become double. So this is I think a typo. This number, we can find the number from some strain gauge book. So this is the model for a strain gauge. They're just showing that there are several sensors which fit the model. This is the model of a thermocouple. So a thermocouple again produces an EMF which is proportional to the difference between the measurement junction temperature and the reference junction temperature. When we'll study thermocouples, we'll see. So the reference junction temperature, if it varies, we are trying to find the temperature that we are measuring. We are trying to place the measuring junction close to the point where we are trying to measure temperature. So the measuring junction temperature is the temperature that we want to measure. But the reference junction temperature may also vary if we just keep it in the ambient. That's why in school you have studied that it's kept in an ice bath to keep the temperature constant. So, if it varies, then it acts as an interfering input. On the other hand, the thermocouple has some nonlinearity. So you see that if temperature if the temperature is small, see these quantities are very small. So suppose the temperature is 1 degree centigrade, then this term is very small. So you may choose to neglect it. But if it is 100 degrees centigrade, then you cannot neglect it, and therefore you should consider this nonlinearity terms. So if you consider, so you see that depending on the temperature range that you are measuring, the nonlinearity term may have to be considered. So this is thermocouple model, and this is an accelerometer model. So all accelerometers, they are so for example, in all rockets, aircrafts, you have an inertial navigation system which tells the pilot how fast it is accelerating, and it also tells whether the aircraft is turning or not. So if you use a what is that called? The thing which flies nowadays, quadcopter. What is it called? Drone.
Quadcopter.
Drone. Quadcopter is a standard drone which has you can buy, and which has 4 fans, and you can by controlling the speed of the fans, you can make the copter fly. So if you have in all flying objects, even in cars, you need to measure its acceleration. So you put accelerometers and gyros in a box which is called the inertial navigation system. So the accelerometer is supposed to be sensitive to acceleration along a certain direction. So this is the accelerometer direction in which the accelerometer is designed to be sensitive. But all accelerometers also have transverse acceleration sensitivity. If it has a strong transverse acceleration, which is in a direction perpendicular to this acceleration direction, it also produces some output with respect to that. So it has some sensitivity with respect to that. Same is for strain gauges. Strain gauges also have some transverse sensitivity. If there is transverse strain, especially due to the Poisson's ratio. So in this case, the transverse acceleration creates an error. So this is an interfering input. And then there are, depending on whether the acceleration is, dynamic, changing very fast, etc., you may like to include a dynamic time constant, which we are not talking about right now. We'll talk about it later. So you see that there are several real sensors which can be actually described by this model. Now, right, so at this point, can we stop for a minute and ask whether there is any question or not? Yeah. Any comments? Let us go to the book. Now, what happens is that suppose it turns out, as I was saying, we have gone to a high distance. Yeah, so we got it to be here. So you see that a large number of instruments claim to be linear instruments. Why? Again, because it is, as I said, it's very simple to use. So so when you describe an instrument, you cannot describe that detailed model. The detailed model is probably known to some people who do detailed experiments, or some people who have designed the instrument. But to a user, the instrument will be described, or the sensor will be described by a set of values. So what are those values? So if you go to buy a sensor, then you will typically encounter these values which are given in a specification sheet. So we will now try to understand the meanings of these typical values, so that when we see a data sheet of a sensor, and this is very critical, I want you to gain that competency that if you read a sensor data sheet, you will be able to make sense of it. You will be able to, so we will do problems on this, that given a data sheet, how do we interpret how much of error can actually occur in a measurement system. So such things you should be able to do. So it's one of the very important competencies that we are trying to gain by doing this course. So let's understand some of these common terms. So the most common term, any sensor you want to buy, probably the first thing that you want to know is what is the range. So what is the range? That means what are the minimum and maximum values that this instrument is supposed to measure. So sometimes it often happens that the minimum value is 0, but it need not always be 0. You know why? Because typically when you are, suppose you want to measure a sensor, you want to make a sensor which will be able to measure 1000 degrees centigrade. It is often, and let's say 1000 degrees centigrade to within plus minus 1 degree centigrade. Now, when you are measuring 100, 200, 500 degrees centigrade, this plus minus 1 degree error is probably meaningful. It is acceptable. But if you use this sensor now, which has an accuracy of plus minus 1 degree centigrade, to measure 10 degree centigrade temperature, then this plus minus 1 degree centigrade error will not be acceptable. Right? So therefore, you should say that you cannot measure this with this sensor that you say, or this with this measurement system that you have constructed. You should say that it can measure up to 100 degrees centigrade with this plus minus 1 degree accuracy. So in that case, in that accuracy range, you are having a minimum value of 100 degrees centigrade. So for these reasons, and could be for other reasons also, maybe the sensitivity of the sensor, I mean the characteristic of the sensor changes. I mean, for example, if you are buying, the mechanisms which are physical mechanisms which are used to, let us say, measure temperatures of 1000 degrees centigrade, 2000 degrees centigrade, are totally different from the physical effects that will be deployed to measure, let us say, 5 degrees centigrade, or let us say minus 5 degrees centigrade. So it could be that the physical phenomenon which is deployed is not effective below a certain range or above a certain range, or above a certain value. So these are, so there is a, in short, it is quite likely that there is a minimum and a maximum value. Often the minimum value becomes 0. So these minimum and maximum values constitute the range. Sometimes only the maximum values constitute, when you only one value is stated, it is understood that the minimum value is 0. So that is the meaning of range. And then there is an associated term called span. So span is the range of values. So it is Imax minus Imin. So it is the maximum variation in the input or output. That is the range of values. Range somehow actually, in English these terms are confusing, but when you say range, it usually refers to a maximum value. Sometimes it could also refer to a minimum value. When you say span, it means Imax minus Imin. So basically, it is also a range of values, but that's the terminology. Now, so these are, this says that over what values of input the sensor is effective, or the sensor can provide measurement of a certain quality. Now, within this range, within this set of values, how we have to describe how the sensor behaves. So we often construct instruments and often give a specification through a data sheet. We are trying to, the manufacturer is telling the customer what is the behavior of the sensor that the manufacturer has manufactured and is trying to sell. So very often the manufacturer tries to give an impression to the customer that the characteristic of the sensor is a straight line. Why? Because again, it's a sort of 10 years later, when everything becomes computerized, this will probably not remain the case. But because everything will be interfaced to a computer, and there will be lookup tables, and it will be easy to put a characteristic of a sensor into a lookup table, and that will increase accuracy, etc. But so far, all instruments are not interfaced to computers directly, and therefore it is cumbersome if you try to describe the behavior of the sensor by a lookup table of 20 values. Then everywhere you have to remember these 20 values. Whenever you get an output, you have to reflect back using the lookup table, etc. When computation becomes very ubiquitous and easy, then it will probably happen, down the line, 5-10 years. But right now, people still try to describe most of the instruments as if its characteristic is actually given by a straight line, because then you have to only remember two numbers, right? Y equal to mx plus c. So you only remember the m and c. So that is why it is considered that the ideal characteristic. We will often think that the instrument can be treated as a linear characteristic instrument. We will often even try that this a value becomes 0. Then I have to only remember k. So I get the output of the instrument, I divide by a number k, and I get the true value. Right? So that's so easy. So from that point of view, the instrument is looked up as a linear instrument. Now, when you are, we'll talk about nonlinearity a little later, but when you are talking about, let's go to, when you are talking about seeing the instrument as a straight line, you have to say what is the value of k. So the value of k is the sensitivity of the instrument. So it is delta O by delta I. Why these deltas are given is because this definition is applicable even if the instrument is nonlinear. But for a linear instrument, delta O by delta I is going to be constant. For a nonlinear instrument, it will not be constant. It will be dependent on the value of I. The slope will change, right? So it is important to understand this sensitivity, because then typically people construct instruments which gives output in a standard range, 0 to 5 volts. So if you have a standard range 4 to 20 milliamperes, these are standard instrument ranges. So immediately you can understand that what is the range of the input. If you know the sensitivity, you know what is the range of the input quantity which you can measure, right? So the sensitivity is generally very important, often very important, and we want instruments to be highly sensitive, but at the same time, you can probably understand that sensitivity sort of restricts the range. If you have a highly sensitive instrument, then you can measure a very small change. That's true. You can probably measure a value, to a very low resolution. That's also true. But similarly, you will not be able to measure something with of a very large range if you have a very high sensitivity, because typically the range of the output that you are going to produce out of the measurement system is going to be restricted. We cannot produce a 200 volts output from a sensor because we cannot read it. 200 volts, we cannot deal with it. So our sensor outputs are typically will be in the range of 0 to 5 volts, 0 to 10 volts, 4 to 20 milliampere. This is the kind of ranges that we use. Okay, these are very, very simple concepts. Nothing very complicated about it. Then we talk about non-linearity, because these specifications you'll find them. Okay, I should not change this in this manner. Then okay. So let's talk about non-linearity a little bit, and because this specification is often given, and So nonlinearity is, what is nonlinearity? See, we have already if we describe the instrument by a straight line, and we say that it has a sensitivity K and an offset A. So this is the line. In this case, the way it is drawn, A seems to be 0. So now when you describe this as by this, but the actual characteristic is like this, then you have to also say that what is the deviation from this line, right? So typically, if this deviation is not too high, then you still want to pass the instrument as, you know, as a linear instrument for convenience. But you want to say that there is a nonlinearity and the effect is limited. So unless you need not really, you know, model the nonlinearity and know the coefficients of these terms, but you can just know what is the maximum deviation that can happen from the straight line. So often, rather than characterizing the we do admit, we say that the instrument is, we are quoting the instrument as a linear instrument, we are giving a sensitivity value, but I also want to admit to the customer that it is a nonlinear, there is some nonlinearity effect, which may not be that prominent. So we don't need to model it. We just want to know, we just want to say that the deviation from linear behavior, as stated, will be, the maximum deviation from the nonlinear behavior will be 2%. So we just say that it is, you can treat it as a linear instrument, but remember that it is actually nonlinear. It's nonlinear. The nonlinear effects are restricted to within 2% of the value. So if you say that, so often for instruments we see such. So maximum nonlinearity. Now this 2% is 2% of what? So you see this nonlinearity can happen. So this 2% of what? So 2% of. So if you can say that it is 2% of full scale deflection. Now you see, now we have to write. So let me write on my board. Okay. Okay. So I shall this whiteboard takes a lot of time to come up somehow. The device is very slow. Yeah, so it has come up. Good. So this was our last day's picture. We have to go to a new board. All right. So you see that I am saying that the instrument is linear. So I have quoted a sensitivity value. So the instrument is quoted as linear with some K. Let's forget about A. Actually, mathematically speaking, this O is equal to Ki plus A is a nonlinear characteristics because it does not obey superposition theorem. So anything so y equal to mx plus c is not a linear characteristic, although we have learned it in school. From a superposition theorem point of view, it is not linear. So, but we are not here. We are taking a more geometric point of view. So to avoid complexity, let us assume that this A is 0. Then both that confusion is gone. So now the actual characteristic is, so if suppose the actual characteristic is like this. It is a parabolic. I'm just drawing. So this is the true characteristics. Now, if we say that now we have to, so there are deviations from the linear. This is the stated or nominal linear characteristics. Now I want to because whatever performance I'll stay in my say whatever performance I will claim in my data sheet, it will be that performance has to be guaranteed. So if I give a nonlinearity characteristic saying that it is, let us say, if I say that nonlinearity is 2% of FSD, full scale deflection, then this is full scale deflection. Well, the diagram is not like 2%, it is exaggerated. So don't bother about that. So then I am saying that my nonlinearity, my reading, so this is 2% of full scale, right? It looks like a cylinder. So when I'm saying that nonlinearity is limited to 2% of full scale, then I am saying that anytime you get a reading, so you get a reading, let's say here, or if you give an input, it actually specifications are, this is another thing, little bit confusing, that specifications are always given. So if you apply a full scale input, then the nominal output is going to be this. Suppose this is the full scale input, full scale deflection, full scale input. So this is the full scale input, and this is the nominal full scale output. This point. So it says that the true output is going to be within 2% of full scale deflection of, so when you are having an input here, let us say half full scale, then the nominal output should be here according to the linear model of the instrument. But it says that it can be anywhere between this and this. It will be anywhere between this 2%. So this is plus minus 2% of FSD, right? So you can see that if you state it like this, what is the problem? There is no problem when the output is around FSD, then the error is only 2%. But when the output is, when the input is, you are trying to measure a quantity which is small, which is 10% of FSD, when the input is like that, then a 2% FSD error will imply a 20% of reading output. So if you are predicting a reading of 10 degrees centigrade, the reading could be in error by 2 degrees centigrade, which may not be acceptable. While if you are measuring an error of 100 degrees centigrade or 1000 degrees centigrade, then a 2% error may be acceptable. So you see that this is the problem. So you sometimes, to avoid this, you sometimes state this nonlinearity or the deviation from the linearity as not as 2% of full scale, but as 2% of reading. So if you do it for 2% of reading, again, this is your characteristic. Then if you say that your error is within 2% of reading, then you are specifying an error bound which is conical. Agreed? Now it is always 2%. So in fact, if this error is, suppose this is 1000 degrees centigrade. And the error is, let us say, 5 degrees centigrade, plus minus 5. Then you have then this error is 0.5% of FSD. Now, but the error here is also plus minus the same, plus minus 5 degrees centigrade, as was the problem. But if I say that the error is 0.5% of FSD of reading, not FSD, then still here I have plus minus 5 at 1000. But here my error, when this reading is, let us say, 100, then I am saying that this is plus minus 0.5. So now if we can specify this, then the customer will see that even at 100 degrees centigrade the error is acceptable. For this specification, the customer will interpret that if I make a measurement of 100 degrees centigrade, then my error will be plus minus 5 still. So it may not be good. So I may not buy this instrument. But if I am able to say that it is 0.5% of reading, then the customer will see that at 100 degrees centigrade, this manufacturer is saying that the error is plus minus 0.5. So this instrument is better. But the question is, can I guarantee it? Because there are some error sources which are due to interfering inputs and they are constant. They don't depend on reading. There are some error sources which are due to modifying inputs. They are multiplicative. Their effects depends on reading. So if I only say, so now I will, point is that maybe up to 100 degrees centigrade I can still manage it, but if I am measuring, let us say, 10 degrees centigrade, then can I say that it is 0.5% of reading? It may not be, because then I need a 0.05 degree error. I may not be able to achieve it because there are interfering inputs. So if I am not able to achieve it, I must not put it in my specification data sheet, because then I'm misleading my customer. I cannot guarantee 0.05 degrees centigrade of error, and I'm trying to put in such a value. So then I can actually, what I can do is I can say, suppose the maximum error I can achieve is, let us say, plus minus 0.5 degrees centigrade. I cannot achieve any more. So I say that the error is so now I say that the error is 0.5% of reading or 0.05% of full scale deflection, whichever is greater. If I give my nonlinearity error specification, nonlinearity is the deviation from linearity, a linear characteristic. So I am saying that if you, there is a nominal characteristic which is given by this number K, sensitivity that I have stated of the instrument, but the readings will vary because of nonlinearity effects. And how much will be the maximum possible variation? The maximum, so if you use it as a linear instrument, then you may be in error. And I am binding that error. I'm saying that the error will not be more than 0.5% of reading or 0.05% of full scale deflection, whichever is greater. So now what happens is, when the reading is high, that means let me take a different pen. So in this zone, the 0.5% of reading, that error specification will apply. And in this part of the, after 100 degrees centigrade, the 0.05% of full scale deflection, which is constant, which is also 0.5 degree, will apply. So effectively, I am saying that the error will be in this cone, and then after 100 degrees centigrade, I cannot reduce the error with reading. So the error will remain constant and it will remain within this bound. So then I have been able to give a, you see that if I wanted to give a 0.05% of FSD specification throughout, I would have failed here, because it cannot maintain 0.05% of FSD in the higher ranges, and it cannot maintain 0.5% of reading in the lower ranges. So I have mixed them up and giving a specification so that these numbers are the lowest. If I wanted to make this, this 0.5%, I would have by a cone, then I would have had to specify a bad cone. Then to a long distance, it can be proportional to reading. Similarly, if I wanted to increase, explain it by only a full scale deflection, then I have to give a bad cylinder. So by giving either a fully conical specification in terms of reading or giving a fully cylindrical error specification in terms of FSD, these numbers become very, very bad, these error specification numbers. And the instrument looks bad. The instrument has to look attractive to the user, only then it will sense. But by mixing my specification strategy, by saying that it is either 0.5% of reading or 0.05% of full scale deflection, whichever is greater, calculate both, and whichever is greater, that will apply. I am able to keep these numbers to small values, and these are error numbers. So if they are small, then the instrument looks good. So often you will find that specifications are stated like this. Let's stop here. This is a new concept which we have talked about, which is not there in the book. This is not there in the book. So let me stop presenting here, and let me ask you, is there any question? Please let me know. Have you followed this? Think about it. Take 2 minutes while I finish my breakfast. Let me project the screen so that you can see it. Look at this. So any question? Everybody understood everything? Great. Thank you. I will move on then. So this is, we have decided, I have told my assistant to upload all these screens, etc. on the I will try to create, we'll tell you presently within this week perhaps, that we will organize our storages into 3 classes. One will be the lectures, videos. If there are any documents, there will be documents. We'll tell you about those things after we organize ourselves. But this is something which is, we are following a book. So I'm telling you that this is something which is not explicitly covered in the book. All right. So let's go back to the book. So these are ways of specifying nonlinearities, right? In some cases, you model the nonlinearity explicitly. A popular way of modeling it is as a polynomial. Now the question is, it's also important to let's go back to the whiteboard. So whenever we are talking about nonlinearity, we have to say that nonlinearity is what? By the way, another interesting thing, let me go to a new board. So nonlinearity is deviation from linearity. Linear characteristics. Okay. But interestingly, this is just tradition. Often nonlinearity is called linearity. It's strange. So a linearity specification is in reality a non-linearity specification, an NL specification. So we often say 2% linearity. Of whenever you say 2%, we have to say 2% of what? So, but interestingly, when we say 2% linearity, it means that deviation is within 2%. Obviously, deviation cannot be, deviation is 2%. So actually it is a non-linearity specification, but it is a common practice to call it a linearity specification. Just for you to remember. Now there are 2 questions when you give these. One is 2% of what? So we have just talked about it. It can be FSD or it can be reading. The next question is deviation from which line? From which straight line? This is the second question, which is very important. When you are stating a nonlinearity specification, it is a deviation from linear characteristic. But which line? So, what is meant by which line? So, you see that suppose I do an experiment with the sensor and I get some points. So, this is input, this is output. I get some point by experimenting. These are all exaggerated drawings, by the way. Now, this is the maximum. This is Imax. So, which is the straight line that we suppose this is I mean 0. So, which is the straight line that I'm talking about? I can talk about a straight line which connects. Let me choose colors now. So I can choose a straight line which connects the maximum reading with 0. I can do that. This is one straight line. How is the straight line defined? It connects the 0 point to the Omax, Imax, Omax point. Just connected by a straight line. What is the advantage? The advantage is that you have to, if you want to determine this straight line, you have to only do one experiment. Just find out the reading Omax for the Imax input. You are done. You got the straight line. Now, what is the disadvantage? The disadvantage is that this straight line, you see now with respect to this straight line, if you have to give a nonlinearity characteristics, you have to give such a characteristic, such a specification that it captures this deviation. So there's a large deviation and your specification will become bad. You'll have to, since you have to enclose this point, every point has to obey your specification. Otherwise, you are not, your guaranteed performance does not occur from your sensor. So if you take this line and try to give a nonlinearity specification, it will look bad. What is my alternative? I could have, alternatively, I could have tried to fit a least square straight line. So I would have actually, you have done this in your physics lab, and I am not deriving the equations, that if you have a number of points and you want to fit a best fit straight line for these points, then you would have possibly given a straight line which is like this. So you should have given this as the linear characteristic, least square fitted line. So obviously now you see that if you want to give your nonlinearity specification with respect to this line, then your nonlinearity specification will look better because these errors are going to be smaller. So it will look as if the instrument has, if you use this line as your ideal linear curve, then the errors are going to be less and the customers are going to like it. But the problem is that now to be able to determine this line, you will have to do so many experiments. You need all the points to determine this line. So finding this line is more complicated. But with respect to this line, the linearity specification will look better. So this is also another important point, that whenever you are talking about, you find a nonlinearity specification stated in a data sheet, it is legitimate to ask or to understand somewhere it will be stated in the data sheet as to which straight line. So whenever you get a nonlinearity specification of X%, you have to know X% of what, and you have to know that the deviation is from which straight line. So that is important to understand. So is this point clear at this point? Any questions? Are you there? Are you listening? I need some. This is the problem of online teaching. You know, nobody knows. You don't know whether there's a robot teaching. You can't see anything. Similarly, I don't know whether you have gone for breakfast. So anyway, you can have your breakfast here. Doesn't matter, especially for you. So Rohit, क्या बात है? Rohit.
Hello.
Yeah. कुछ बोलो भाई.
Sir, it is clear, sir.
Say something.
Hello, sir. Can you hear me?
So I remember, you know, these are great experiences. So I remember I was taking a control systems class way back, I think maybe 10 years earlier. Control system class is large. So I was in, so kya hai wo, I think it's V1 or V2, one of those large classes. So a lot of people comes in, so I tell them, mic not working, sir. Good. So so we were waiting, because you can't start at 250. Thank you, Rohit. So mic is, I mean, you have to wait till about 25, 30, 40 people come. It's a 200 strength class. So I was waiting. There is a Sardar sitting in front of me, getting bored. People are slowly trickling in after breakfast. Hall mein nahi milta. So always 8 o'clock classes are delayed. So I told the Sardar, what was his name? I don't remember his name. So let's say Bhupinder. So I said, Bhupinder, say something funny. Bhupinder looks up at me with a very stern face and says something funny. Can you believe that? It's not funny, right? This is another thing. You try to say something funny, which you think is funny in a class. You will meet a set of faces. Some will be blank. Some will have a look saying, "What is wrong with you?" I mean, etc. So no comments. Thank you. Let's move on. So I guess this is clear to you. These are important, because we are going to interpret data sheets. So these are important points to remember. Data sheets are large things. They are actually complex. We will actually try to interpret real data sheets. So you have to remember these, and you have to carefully look into a data sheet. Reading a data sheet is not easy of anything. We have complex objects. So, understanding specifications of complex engineering objects is a basic competency of an engineer. So, go back.
Sir, I have a doubt.
Good.
Sir, so I do not understand what is the significance of this line specification to the end user. Like, for example, if they know that from which line it is deviating, then how will they make sense of that information?
Right. So there are. So we'll. So to answer your question, there are the first thing is that from time to time a user may be required to do a calibration. Right. So firstly, it is I mean, if you take an instrument and if you assume that the line is given and the instrument for your complete period of usage, if you know that it's not going to change, you can simply go on using that specification. That is one scenario. Another scenario, which is very common in manufacturing, is that sensors, particularly sensors, will have to be calibrated. You see, the whole quality of manufacturing very much depends on the accuracy of sensors. If you are manufacturing, let's say, an engine block through which a piston will move, the piston, when you are machining the piston or when you are machining the engine block, you have to maintain great accuracy so that the diameters are exactly as it should be, so that if they are most very tightly fitting, then it will cause heating, it will cause friction loss, engine power will be lost, and it will cause heating. If it is more, I mean the engine block bore, if it is more, then the engine then the engine pressure will not build up, gas will leak, etc. So these measurements are very critical, and therefore there is a, to maintain quality. For example, if you go to let us say ISO 9000 specifications, you will find ISO 9000 specifications are actually quality certifications. So if you are buying from a manufacturer who is ISO 9000 compliant, why customers go there? Because customers know that they are ISO 9000 compliant, certified by independent agencies. So they have a process of manufacturing which ensures quality. So if you read ISO 9000 specifications, you will see that a good part of it is actually about keeping your instruments calibrated. So when you calibrate your instruments, you will know that when you take readings, or if you even give it to a calibrating agency, the agency will come back to you with readings. So now you can actually see that whether the specification with you purchase that instrument with some expectation, right? Some expectation of error. So when you get back the readings from your calibrating agency, you can actually see whether your error specifications which were originally there are being met. So for such purposes, it is important from time to time. If you are a manufacturer or if you are a calibrating house, then also you will require it. So you are right in the sense that if you are just normally using, then you may not know it. It's some straight line. But in some situations, it is better to know that so for example, if it is a straight line which has been fixed with the maximum point and 0, then you know that the error around the maximum point is actually going to be low, because the straight line has been fixed with respect to that. But if you are doing a least square fit, then you know that it may not be. Possibly then typically what happens is that there is a larger error on both sides, and the error in the mid range is low when you do a least square fit. So these are the implications, but otherwise what you're saying I would accept. So I don't know whether this makes sense to you, what I said.
Yes, sir, this answers my question.
Yeah. So let's move ahead. So in some cases, for example, in particular in case of thermocouples, often this is the way it is stated. So these polynomial curves are given by manufacturers, especially when your temperature range is large. Then these terms tend to become large, and then these nonlinear terms will have to be considered. So that is another way of, and these nonlinear terms are again these. I mean, how do you get these? How do you get these coefficients A0, A1, A2, etc.? In the case of these, polynomials, fit. These are typically fit again by a least square method, which is again similar. So, right. So this is the interpretation of nonlinearity. We go forward and quickly see some other terms which are also applicable for certain other classes of instruments. You see how here they are saying that this X% of FSD and Y% of reading, whichever is greater, this thing, I mean, typically the Y% of reading comes from the manufacturing, comes from the modifying inputs, because they change the gain, so the error is proportional to the reading, and the X% of full scale deflection kind of specifications come from the interfering inputs because they are constant. So that's what is being explained here. Then comes hysteresis. There are some devices where the hysteresis can be considerable. So normally we expect that in a hysteresis at the same value. So what is hysteresis? We all know hysteresis, I mean magnetic hysteresis. So so it means that if you are increasing the readings, then you will get a characteristic like this. When you are returning and decreasing the input, then the readings will come through a different path. Oops, now it fitted, I don't know why it fitted a triangle. These things are becoming intelligent. I don't mean a triangle. Now this guy has fitted a triangle. Just imagine. So anyway, so this is a nuisance actually. Too much intelligence. Why did it fit a triangle? I didn't mean to fit a triangle at all. See, look at this guy. This is funny. Anyway, I never saw this. It was not there in my previous version. Is this software updated? I don't know. I never encountered this. That I'm trying to draw a curve and it is fitting it to a rectangular this thing. How do I get around this? Any way to get around this? Lasso select. What is that? So anyway, so so if this paths are significant, then you can understand that we cannot say what is the output value for a given reading, because they may be different depending on whether the input is increasing or whether the input is decreasing. So for a system with hysteresis, the value of the output when the output is decreasing and the value of the output when the output is increasing are different. And the definition of hysteresis is their difference. So if sometimes if some sensor, like even magnetic sensors, or sometimes membranes, etc., so they have elastic hysteresis. So this could play a role. So in some sensors you may find this specification. That's being said. Resolution is a very important specification. And so resolution is, it says, this is again hysteresis. So hysteresis is very prominent for gears, but we don't typically, at one time people used to use gears in instruments because a lot of mechanical things used to be there in instruments. Nowadays they are absent. So in resolution it says, what is the resolution? Resolution is the smallest change in input that you can measure. Remember, smallest change in input. So it is resolution is the smallest change in input. This term is important. It is not the smallest input. It is the smallest change in input. And there is a difference. because particularly, you know, things which used to have friction and other things, the smallest input could be high because of, you know, static friction, etc. But smallest change in input is from any input I, you are getting an output O. What is the smallest amount by which the input should change so that you will get a definitely detectable change in the output, right? So that is this term may be affected by the noise environment of your sensor. If the readings are noisy, so, you know, people sometimes say that, you see, we have 64-bit processors. Why we do not have 64-bit AD converters? Why AD converters are almost always restricted to 16 bits, 18 bits? That's because if an AD converter has a 10-volt supply, then a 16-bit means 10 by 2 to the power, that means 64,000. So 10 by 64,000 is the equivalent analog voltage for 1 bit. What is that? What is 10 by 64,000? 10 by 10,000 is 100 millivolts. No. 10 by 10,000 is 1 millivolts. 10 by 64,000 is 1 by 6 millivolts. 1 by 6.4 millivolts. If you make it to 18, then it will be 1 by 25 millivolts, which is like 40 microvolts. So the question is that your noise settings may be such that your noise amplitude cannot be restricted to, you know, 1 microvolt, 2 microvolt. That may be too expensive to do. So if your noise is limited to, let us say 100 millivolts, then there's no point having an 18-bit AD converter, because the last 3 or 4 bits will be simply dancing because of noise. So you don't have a resolution. So so an input change of, you know, 50 microvolts cannot be reliably sensed, because the bit pattern, which is the output of the AD converter, will be simply random. So this is one example. There are some sensors which are inherently discrete, like they have given an example of a potentiometer. So a wire wound, a coil is wound, and on this you have some wiper. So the wiper is either, I'm just showing here, normally wipers are connected to multiple windings together, but imagine this situation, even if it's connected to, you know, 2 windings, it does not matter. But look at this wiper. The resistance that it connects into the circuit, this potentiometer, naturally changes in steps, because it either connects to coil number n or coil number n plus 1. So there is a resolution. There is a smallest change in input which can be considered. If you have an input, if you have a motion change smaller than that, then there will be no resistance change, because the next coil will not be connected. So this is the sense of resolution. So resolution can happen either due to a really discrete sensor. It can also happen due to a noise specification. But there are some sensor manufacturers which want to explicitly, you know, for example, position is measured by potentiometer. Position is also measured by a device called LVDT, linear variable differential transform. It's very much used for measuring position. So now the LVDT fellows, when you typically see a specification of an LVDT, the LVDT specification often says that its resolution is infinite. They just mention They write in their data sheet, because everybody wants to brag and boast. So the LVDT fellow says, well, you can go and buy a potentiometer, no problem. But remember that the potentiometer has a finite resolution. My resolution is infinite. So what does it mean by that? It means that because it's the principle of measurement of position is by electromagnetic induction, the transformer principle. So therefore, theoretically speaking, an infinitely small change in the position of the magnetic core in the LVDT is supposed to make an output change. Now there may be noise, and that output change may not be discernible in practice. But just to emphasize the point that they do have the output is supposed to change ideally with respect to an arbitrarily small change in the position of the magnetic core, they will say that the resolution is infinite. So I have seen that happen. So this is resolution. Okay, wear and aging, those things we'll see, because everything degrades. And there's incidentally in the modern world, there is a huge interest to track degradation of equipment. So when we put wind turbines are installed in very difficult to reach places. They're either kilometers into the sea because the wind is there, or they're up on a hilltop where there is wind. So, and they have large blades which are always which always face gale-like situations to generate power. So engineers are always trying to understand that what is the health of so health monitoring has become a major area of research and technology. So from aircraft engine to wind turbines to all kinds of manufacturing stuff, we always want to understand that what is the condition of my cutting tool, whether it guarantees a certain surface finish, whether I have to take a scheduled maintenance of my milling machine. We want to understand beforehand. We want to know when my car battery is likely to fail. So for these kind of scenarios, it's very important to track the degradation of equipment. So even for sensors, particularly for electronic circuits, if you see an amplifier specification, you will see various kinds of drifts in any amplifier. And again, most sensors have electronic circuits, including amplifiers. So electronic circuits typically have drift specifications. And these drifts are stated, that means the characteristic which is stated will change. The manufacturers say, change with respect to what? So they change with respect to typically two things. One is change with respect to temperature. The other is change with respect to time. So change with respect to temperature is actually an interfering and modifying input effect, while change with respect to time is due to material degradation, and that's kind of random. So these specifications you will always find in, particularly in sensitive electronic circuits. So since electronic circuits, so they could also be part of a sensor. Coming to now we come to another point. That point is that so now we are familiar with this model of an instrument. But now the question is that now sometimes what happens, you see that these instruments are manufactured, right? So when a data sheet is given, it is not given for one specific instrument. It is given for a class of instruments which is manufactured. So I don't know how many of you know that there are, when you go to buy an electronic component, there are commercial grade components. There are industrial grade components. There are military grade components. You can buy a resistor, you can buy an amplifier of either commercial grade or industrial grade or military grade. And military grade components can be easily 10 times more expensive. Why? It's the same amplifier. Any idea? Anybody has heard the term mil grade? So all defense equipment are always manufactured with mil grade equipment, mil grade components. Why? And what is special about these components? Anybody knows this? Come on, somebody must be knowing. Vikram? Any idea?
Yes, sir. Like the military grade components are used by the military. Like they may be used in varying temperatures, varying heights, varying pressures. So like they are of high standards.
They are of high standard.
Like they are used in like extreme conditions. Like they may be used in high pressures. They may be used in like.
No, I'm saying that no. I'm saying that. So fine. So you want to say that they will work? Yeah, you are right. So typically you will find temperature ranges for commercial grade equipment and temperature ranges for industrial grade equipment and temperature ranges for military grade equipment are different. You are right. So military grade equipment, when you are manufacturing, you manufacture through a similar process, but suppose you have manufactured 10,000 of them. And you are saying that this amplifier will have this much of gain over a temperature range of -30 degrees centigrade to, let us say, 80 degrees centigrade. So if you take of these 10,000, if you really perform an experiment with all of them and take them from -35 to +80, you will find that probably 85 of them will, their gains will vary. Their gains will not remain within that range, in that temperature range. Only probably 5. So, and then 10 of them will probably be within range for the industrial grade equipment, and only 5 of them will be in range for military grade equipment. So now you have made 10,000 components from a process. You do these experiments and you classify them. So now this 85%, you use them as commercial grade equipment over a small temperature range and you sell them cheap. The rest 10%, you sell them as industrial grade equipment for higher temperatures, more robust, and only 5.5%, the 5 out of 10,000 which survived this temperature range and still was of the same characteristics, you will sell as mil grade at a very high price. So you see, what I'm trying to say is that when you are manufacturing things in a batch and you are trying to specify them, you are trying to write a specification in a data sheet. So you are specifying a batch of components. Therefore, you must provide a statistical specification. So this is important now to understand that even for sensors, there is a statistical specification possible. So that's what we are going to look at now. Because they will characterize, so this is the statistical characteristic. What is the statistical variation in the output of a single element? What is its repeatability? So if you take a sensor, let's say they say that if you take 10,000 sensors and bring them and try to measure the temperature in this room right now, they will not show that's exactly the same reading, right? So even the input of a single element, if you try to measure them at this, measure the same thing for, let us say, several days, then also the reading will not be same. So this is called repeatability. So if you take a sensor and take the reading of the same input under similar conditions, similar to the extent you cannot ensure exact similarity. Somehow maybe the temperature is going to be different, ambient temperature may be different, there may be some humidity change, there may be some voltage change which if you have connected the sensor to a power supply, there may be somebody maybe welding somewhere nearby when you are making a reading, so there may be some electromagnetic interference. So there are all kinds of random things happening and you cannot take care of everything. But what you observe is that you are making apparently the same measurement, the same maybe junction temperature of thermocouple you are measuring, but you are getting a slightly different reading every time. And depending on how close a reading you are getting every time, an instrument is called repeatable, right? So repeatability is the ability of an instrument to the closeness with which it can produce readings multiple times when measuring the input of the same value. And naturally, if an instrument has to be repeatable, then it has to be immune to interfering and modifying inputs. And so that number one, and number two is that so basically the effect of interfering and modifying inputs will not be much. There are some instruments, for example, they have given an example of a vortex flow meter. So when we study vortex flow meters, we'll see that vortex flow meters put an obstruction in a flow field and create vortices. And these vortices create they create vortices which create a vibration in a sensor of a certain frequency. But as you can see that these flow streamlines are kind of random. You cannot when a stream is flowing, especially when there's turbulent flow, then the streamlines are all random quantities. It's somewhat like electron motion. You cannot. They have a statistical property, but individual streamlines are not. They are actually random variables. So the vibrations they will induce will also be random, and the frequencies of those vibrations will also be random. So the whole principle of measurement of the vortex flow meter is actually statistical. So you can never get a constant frequency output. But the question is that if you put them in a turbulent flow field of a certain flow velocity, then the frequency of vortices are going to be random, but they will be random around a mean. And how closely they vary around the mean decides its repeatability. So repeatability is actually a very desirable property of an instrument, right? So you see, these are all deviations. So nonlinearity is a deviation around some nominal straight line which is defined. Linear repeatability is again deviation from the same straight line, but not due to nonlinear effect. It is due to effects which are not accounted for, random effects. So that's also a deviation that will also add an error to from the nominal straight line. Similarly, resolution will also add, because there may be inherent resolution problems, like the case of the potentiometer. So when you have a sensor together, which has a nonlinearity specification, which has a repeatability specification, which has a resolution specification. You have to understand that due to the effects of all these things in a given circumstance, what kind of errors you will get, right? So these are all, small deviation specifications, but they're due to different reasons. Nonlinearity is due to you have simplified the actual model for ease of use. Something is really nonlinear, you are calling it linear, and then saying that it actually deviates from linearity. Repeatability is due to an entirely different effect. It could be. Even nonlinearity can be due to the variation of, because you have ignored, interfering and modifying inputs. But there may be some interfering and modifying inputs whose effects you have considered, and there may be some whose effects you haven't considered. So repeatability is typically due to those which you haven't considered, right? So when you are interpreting data from a sensor, you have to be very, very careful. Otherwise, you have to know all these to be able to interpret the data that you are getting, or to be able to characterize the kind of expectation of accuracy from the sensor that you are getting, right? So so now we have got this we have got the input-output equation. So the input-output equation of the output O. So we have got this input-output equation. We know the input-output equation. It was just shown on top. This is the input-output equation. This is the input-output equation of an instrument, right? Now, if you take such a model, and then try to find out that what is the effect of variation in these parameters. So what you can take the effect of anything in that equation just by the laws of mathematics. So you can find what is the derivation, what is the deviation in output due to the measured input, due to the interfering input, due to the modifying input and the interfering. Now the point is that you may not be measuring. This is what you are trying to measure. This is your desired thing. So you are very interested in that delta I. You are actually trying to compute that delta I. But these you may not always measure. You may not have, when you are measuring the, let's say, the temperature of something, water, using a thermistor, you may not, you are not almost always. So for example, when you are trying to, so you may not measure the ambient temperature. You may not measure some other modifying inputs. So when you are measuring the strain of a strain gauge, you don't measure the ambient temperature. Why? Because the output due to the strain is supposed to be much larger than the. I mean, you sort of ignore it. You are weighing a truck. Since you are weighing a truck, the major input is strain gauge. Strain input is actually coming from the weight. So whether you are making the measurement in summer or winter, that correction you may not do. You may choose to ignore it. On the other hand, if you are trying to measure gold, I don't know whether you have ever gone to a goldsmith shop. I have seen that, first of all, the scale is, nowadays they use these things even for normal mithai ka dukan, sweetmeat shops. So you will see interesting things. You will see that suppose you have gone to buy curd in a sweetmeat shop. You have a digital scale, right? So that guy will in these parts of the country, in Bengal, he will always have an earthen pot. So he will put the pot on the scale first, empty pot. Then he will do zero error correction. So he will set the zero so that you get a display. You have to show to your customer that you are getting the right amount of curd. So he will make a zero error adjust electronically in the instrument, and the weight of the earthenware pot will be taken as 0 now. Then he will put the card in the pot, and then he'll weigh the pot, and you will get only the weight of the card because the weight of the pot has already been subtracted by doing a zero adjust. So in their output model, they have now included an A term. They have included a KI plus A, that A term. They have included just by pressing a button because it's a digital meter, right? On the other hand, if you go to a goldsmith shop, then the weight of the gold is so precious. So firstly, the scale is going to be within a box, because if it is kept open, then a running fan which can create some thrust on the pane on which the gold will be placed can actually create an error. So the fan speed now becomes an interfering input, right? So, but we are not measuring the fan speed. So what I'm trying to say is that in a typical measurement situation, you are interested in this, but you always may not measure this delta IM and delta II. So they may be, sometimes they may be treated as random. When you don't measure something and still want to understand its effect, you say that, okay, it can be anything, but limited to this. So you often model them as the whole of statistics. What is a random variable? A random variable is something where when you toss a coin, when head will come and when tail will come, it will depend on the exact force that you are applying on the coin at that point of time. It will depend on the air density, it will depend on the air humidity, etc., etc. And you can actually calculate solve a differential equation and then get that for that particular throw whether you will get a head or tail. But that's not possible to do. So therefore you choose to describe the output of that coin tossing experiment as random, and you say that I don't know. Sometimes it will be head, sometimes it will be tail, and you take that into your stride for your future decision making and application. That's why the whole field of statistics comes, because there are things, everything cannot be measured. So exactly here, by the same argument, you can have these, or sometimes you can treat these as random. So now, if you have these as random, even if you have, now you can apply, statistics, and you can calculate standard deviation of the output and things like that. So if you consider that the random input delta I is independent, statistically independent of delta IM, which may not be true always. You have to be careful. For example, if temperature is acting both as an interfering and a modifying input, then you can never take the interfering and the modifying input to be independent, because they are the same value. So they are not at all independent. In fact, you have to, in that case, you have to add these terms. You have to add delta O by delta IM plus delta O by delta II and consider it as a single term. But in some cases, if they are coming from, if you have a power supply variation as an interfering input, and if you have a temperature, ambient temperature as a modifying input, then you can possibly consider the temperature variation and the power supply voltage variation as statistically independent random variables. So if you happen to now do such an analysis, and we are coming to the end of the class and we'll continue, then the theory of random variables say that for the independent random variables, the output standard deviation can be given in terms of the individual standard deviations by such a formula, which is well known. So now, if you see the output as a random variable, because then the output, in fact, you know, the input, suppose you are saying that, suppose when you are doing a calibration experiment, so you think that you have created in an oven, you have created a temperature of 200 degrees centigrade, and you are trying to calibrate a sensor. How do you know that the oven is at 200 degrees centigrade? Possibly because you have another temperature sensor in the oven, which is much more accurate, on which you have a lot of confidence, and that using that you think that you have created a 200 degree temperature in an oven, and then you are trying to see that some other temperature sensor, what reading it gives. But that 200 degrees centigrade that you have measured using another sensor itself may have some variation. So in that case, your input that you think you have applied will have a mean value. Its mean value is 200 if your instrument is good, that other instrument is good, but still it may have its own uncertainty, and then there may be an uncertainty in this. If you want to ignore this, if you think that whatever the instrument is giving is absolutely accurate, if you make that assumption, then the sigma square I is going to be 0. On the other hand, you may have very rough idea. For example, you may read from the newspaper or from the IIT KGP website what is the temperature today, and put that mean value here. Then you know that when you made the measurement, there could be a lot of deviation. So here you can assume a value, so by which you may have gathered by doing some experiment 2 years back around the IIT campus. So these are just, you know, ways to have an estimate of uncertainty of a measurement, and the estimate of to what extent you will be able to estimate the uncertainty depends on how much effort you are actually prepared to make, how much effort makes sense, what is the old data available, and all that. But in any case, if you have some idea, then you can characterize the output of the instrument also as a random variable whose mean will be given by this. Here all the bar quantities are the corresponding means, and the standard deviation quantities are so the standard deviation of the random variable of the output will be given like this, right? So possibly if you assume this to be Gaussian, which is usually a reasonable assumption, but there's no you know, you not necessary to model it to Gaussian. So then you can characterize the variation of output in using this. In fact, you know, you can even, it's not only that you need to you know, take these standard deviations with respect to only the input quantities. You can take the standard deviation with respect to other, you know, parameter variation, especially when you are talking about a batch. Let us say a batch of instruments. Here, your previous case, we were talking about making a measurement with a given instrument. So we are considering variations of, you know, interfering and modifying inputs. Now consider another situation that I have made a circuit, let's say a differential amplifier with 4 resistances, and I have bought the resistances from the market. Let's say they are of commercial grade. So the manufacturer specifies what is the mean value of the resistance, what is the mean value you can get from the color code, and what is the deviation, 5%, 1%. So if you have made an amplifier with those resistances, you can calculate what is the variation of the gain of the differential amplifier using those resistances statistically. So similarly, when you have sensors, so that's exactly manufacturers. So when you read a manufacturer's data sheet, you have to remember that they are specifying values which are mean values of the various parameters, gains, sensitivity, range, linearity, non-linearity. These are all they are stating for a population, for a batch of quantities which they are measuring. So they are statistical descriptions. Now, when you use these sensors in a measurement system, as we have seen, we have a sensor, we have a signal conditioner, we have a signal processor, we have an application module. So now you have a measurement system like that. So if the sensor has certain statistical descriptions, and if the signal conditioner has certain statistical descriptions, and if the signal processor has certain statistical descriptions, then when we couple them together, what is the statistical description of the overall measurement system? That is very important to find out, right? So in the next class, we will talk about this. That means we have come to the end of chapter 2 almost. We have covered it, and in the next class we will see that how if you take these individual blocks of signal conditioners, recorders, let us say pressure to current converters, temperature sensor. If you take these things and join them together to make a measurement system, from the individual specifications, how can we understand what will be specifications of measurement systems? So this is also a very important thing, and we will go into that. So I think we'll stop here today, and I'll stop presenting first, and so let me stop presenting. Yeah. So tell me, does it make sense? You want me to do something? You want me not to do something? There's something you did not understand. You tell me something before we call it a day. Is there any question? No question? It's a long class. All right.
Sir, why are we approximating every process as a Gaussian process?
Because Gaussian processes are very commonly seen. Simply because if you want to, don't you think that if you want to, suppose you set about making 10, suppose you are cutting paper. You want to cut a paper strip of 5 centimeters. You are carefully cutting with some scale. So if you cut 200 such, what do you say? Paper strips, and then measure their length very accurately, what distribution do you think it will have?
Closer to me. Yeah, something like normal.
So so you will have most of the strips which are very close to 5 centimeter, which you wanted to cut. There will be hardly any strip which is 5.2 centimeter or 5.1 centimeter. There will be nothing. So I think from my estimation, the sigma is going to be probably 1 millimeter. Okay, that's the typical sigma of. So you will hardly find any strip which is more than 2 millimeter or more than 3 millimeter off. So it naturally comes. That's why we assume it as Gaussian, and then we have found that mathematically it gives various kinds of nice properties. So if you take a Gaussian random variable and propagate it through a linear system, then the output random variable after filtering through a linear system also remains Gaussian. So you get these nice mathematical properties with which you can do people like me who write papers find it very convenient. So that's it. Nothing else. Yeah. So if there's nothing else, if nobody has any question, those who do not have question, please leave. You may have another class. Thank you very much. Thursday's class is not there because Thursday is a holiday. It's Muharram. So our next class is on next Monday. Bye bye. Those who want to leave, if anybody wants to discuss anything, you can. I'll wait for some time till people leave. But is it okay? I mean, is there anything that I'm doing wrong you don't like, or is there something that you like me to do? Can you, if you can tell me that? Dasari Sai Nishant, are you there?
Yes, sir.
Is there anything that you would like me to do or not like me to do?
So I feel it's going good.
Huh?
So
Bolo,
I
bolo.
feel it's going good.
You feel it's going good? उसका क्या मतलब है? पता नहीं. So I mean, nothing comes to mind. Krishna Pasala, any comments? Something you want me to do, something you don't want me to do? Krishna? No. Ah. All right, most people have left. Let me leave also. If you don't mind, I'll leave if you have no questions. Thank you very much.